Hello. In this video, I will be solving two problems from section 14.4, which is about tangent planes, linear approximations, and in particular differentials. And the problems we'll be solving are as follows. So one is from the problem set 3 to 10, and it wants us to find an equation of the tangent plane to the given surface at the specified point. And the equation we will be doing today is number 6, z equals y squared e to the x. And the second problem we'll be doing is from the same section. This one's from set 31 to 38. And this one wants us to find the differential of the function. And our function for us will be z equals x times ln of y squared plus 1. Okay. So first, for this problem, we need to recall what the equation of the tangent plane is, which I'll write over here. So this equation is z minus z naught equals partial derivative with respect to x, evaluated at x naught y naught, times x minus x naught, plus partial derivative with respect to y at x naught y naught. And let me make some space. Times y minus y naught. And here, the point x naught y naught z naught is the point where we're computing the tangent line. So in our case, x naught y naught z naught would be this point right here. Okay. So first thing we need to do, as we can see from this equation, is we need to calculate these partial derivatives. So doing that over here, well, I'm going to denote these with Leibniz notation. So first, partial z with respect to x. We just fix y, we hold y constant, and we differentiate with respect to x. But the derivative of e to the x with respect to x is just e to the x. So this is y squared e to the x. And therefore, partial z with respect to x evaluated at the point 0, 3 here. So note that we're not going to plug in 9 because that's just our z coordinate right here. We are plugging in the x and y coordinates though, because at this point is where we compute the partial derivatives. So at 0, 3, we get 3 squared e to the 0, which is just 9. And we can proceed similarly with the y derivative. So this is, now we fix x, we make it constant, so e to the x is a constant. And we differentiate with respect to y. We get 2y e to the x. And therefore, partial z with respect to y at our point 0, 3. This will be 2 times 3 times e to the 0, which is 6. And so putting everything together, the equation of our tangent plane will be z minus, z coordinate is 9, so that's z minus 9 equals partial f with respect to x evaluated at 0, 3. And then we subtract the x coordinate 0 plus partial derivative with respect to y at the points 0, 3. Or actually, to be consistent with my previous notation, let me write this like this instead. So therefore, just moving everything to the side, over here we also evaluate at 0, 3, and it's y minus 3 because our y coordinate is 3. And this works out to be, well, it'll be 9x plus 6y minus 3. And this would be our equation of the tangent plane. If we wanted to, we could simplify this a bit, just make it look like a function of z. And this would look like 9x plus 6y. And then 6 times negative 3 is negative 18, plus 9 is negative 9. So this will be z equals 9x plus 6y minus 9. But I think it's okay to just leave it like this. All right, so that's the first problem. Let us now move on to the second problem. Hello. So now we're going to find the differential of this function. And just as a reminder, the differential of a function z equals f of xy. This is dz, which is given by partial f with respect to x times the differential dx, plus partial f with respect to y times the differential dy. So once again, we need to calculate some partial derivatives. Working these out, partial z with respect to x, this is just ln y squared plus 1. And partial z with respect to y is going to be x times 1 over y squared plus 1 times 2y by the chain rule, which we can simplify to be 2xy over y squared plus 1. And therefore, our differential is going to be dz equals, just plugging everything into this formula. It's going to be ln y squared plus 1 dx plus 2xy over y squared plus 1 dy. And we're finished. Not so bad. Here it's just calculating partial derivatives and remembering the formulas for the differential in this problem and for the tangent plane in our other problem. But beyond that, there's nothing new from what we have seen with partial derivatives. All right, that wraps up this video. If anybody has any questions, please feel free to leave a comment. Otherwise, I will see you all in the next video.